Let's look at some trig substitutions now to solve these particular questions here. And this is one, we have a look at this one. We've got the square root of 4 minus x squared. Now there's nothing else going with it. So it can't be a reverse chain rule type of question. So it really, the best way to do this is to attack it with a substitution. You'll see when we do the x equals 2 sine theta why it works out as a good substitution. So if x is equal to 2 sine theta, dx is 2 cos theta to theta. So we change our values because it's a definite integral. 0 to 2 becomes 0 to pi on 2. So we do that substitution in there. So 4 minus 2 sine theta. You see why 2 sine theta was chosen as well, because we get the 4 minus 4 sine squared theta, which the 4 will factorise out. So that gives us the 1 minus sine squared theta. All the while we've had the dx being replaced by 2 cos theta to theta, and that stayed right down there. And we get the 1 minus sine squared theta becomes cos squared theta, which doesn't look very nice because that starts to simplify nicely to 4 cos squared theta. Notice we can take the square root of cos squared theta, which was cos theta. We already had a cos theta there, and then that becomes cos squared theta. Now you can do the integral of that by changing it to a half 1 plus cos 2 theta, and then integrating, substituting our pi on 0 on pi on 2 to get to pi. Now, I don't know, hopefully you've looked at that and go, well, does that function look familiar? Hopefully it looks familiar, because if we graphed it up, and this is just the way you could probably, I would look at doing this question, rather than a substitution. And we're looking at from 0 to 2, that'd be minus 2. That's actually a semicircle. And when we take the integral, well, we're looking at the integral there would be the area of that, which is really just a quarter of a circle, which has a radius of 2. So the area would be a half times pi times the radius squared, which is 2 squared, which would give us 2 pi. Now, is that what we got at the end? Oh, we got pi. Why did we get pi? And I might have to check this again. So 0. Oh, I said a half. It should be quarter. It was a quarter of a semicircle. Quarter of a circle. So there we go. It should be pi. So there we go. Simple error. Be careful. But there we go. That's much easier than doing all that trig substitution. And that would be okay. If you're told to use the substitution, you have to do that. But if you're just told, evaluate that, be wary. That's a square root of 4 minus x squared, which gives you the semicircle. And you can do it that way. That's quite legitimate. Let's have another look at another one where we're using the substitution. Again, if you look at that function, you're looking and go, wait on, that's similar. It is. Same, it's going to give you, that'll give you a semicircle. But let's use the substitution, and we'll have a look at the semicircle to make sure we're right. 2/3 sine theta is our substitution, so dy is equal to 2/3 cos theta to theta. When y is 0, sine of theta gives us 0, so theta is 0. And when y is 2/3, we get sine of theta is equal to 1. So we've done our substitution. Y is 2/3, so the 2/3 cancelled. So pi on 2. So there's our substitution there. 0 to 2/3 becomes 0 to pi on 2. 2/3 sine theta times 9 all squared. The 9's cancel. And I can factorise that 4 out and take the square root. It gives me 2. So that's we're looking there. We've got the 2/3 cos theta. So the 2/3 times 2 becomes 4/3, and that's cos squared theta underneath. So we take the square root, multiply it by the cos theta, gives us cos squared theta, and we're doing like we did before. Cos squared theta becomes 1 over 1 half outside of 1 plus cos 2 theta. And then we're able to integrate that function to theta plus a half sine theta. Substitute 0 to pi on 2, and it gives us pi on 3. So there we go. That's similar to what we were just talking about. That's 1/4 of a radius, a circle that has sorry, it's not a circle. This is an ellipse in this case. But it's a 4 minus 9 y squared. So same idea. Then we can do that and get the area of pi times 2/3 times 2. And a quarter of that would be, because that's the area of our ellipse, and a quarter of that would be pi and 3. So this, you can see how that one worked out as an ellipse. First one worked out as a circle. But again, if you're just asked to find that integral, you could do that. That's not a problem. Let's have a look at this one. X squared on 1 minus x squared to the power of 1.5 or 1.5. We were told to use the substitution sign of theta, where theta is between minus pi and 2 and pi and 2. So there's our limits of integration there, and we're told theta is between that, so that becomes our limits of integration. We don't have to do any calculation, which is nice. Dx here becomes cos theta to theta from x is sine theta, so that's where we get the sine squared theta, 1 minus sine squared theta to the power of 1.5 cos theta to theta. Now the cos squared to the power of 1.5 becomes cos cubed, which becomes sine squared on cos squared when we clean it up, with minus 2 and minus pi and 2 and pi and 2, which we can start to simplify by writing 1 minus cos squared theta on cos squared theta, because you don't really want to integrate tan theta. It's a little bit harder, although doable, and it should give us the same. But 1 minus, that gives us 1 on cos theta, which is sec squared theta, and we've got the minus 1, which we know is equal to tan squared theta anyway. So tan squared theta, as I said, would be hard to integrate. This is much easier to put it in that form, because sec squared integrates to tan theta. Minus 1 would integrate to minus theta. Between the minus pi and 2 and pi and 2, we substitute it in. We get tan of pi and 2 and tan of minus pi and 2, which would be minus tan of pi and 2, and the minus there, they'll start to cancel all out. And we get the minus pi and 2 plus the minus pi and 2, which gives us minus pi. Question 4 here, we're evaluating 0 to 0.5 of the square root of x on 1 minus x. The x, with a substitution of x is equal to sine squared theta. So dx then would be, deriving both sides, 2 sine theta cos theta to theta. So when x is equal to 0, do the substitution, theta must be equal to 0. When it's a half, we can solve our equation there. We get 0 is equal to pi and 4. Do our substitution, sine squared theta over the 1 minus sine squared theta times 2 theta, sine 2 theta to theta. So again, that'd be cos squared theta, and the square root, and we take the square root of both, gives us sine on cos, which the cos's cancel and gives us 2 sine squared theta, which makes it nice. That becomes a half minus 1 cos 2 theta. That's the transformation of sine squared theta. The 2 obviously cancels with the half. Now we can integrate, substitute our values, and we get the pi and 4 minus a half. So there's some examples of doing a trig substitution. A lot of times a trig substitution will be given to you, but if it's not, then you're quite fine to be able to use a trig substitution if you like. But a lot of times you'll do that where you see a square root being put in. We got a square root, and it's not working out to be a nice reversal of a product, of a chain rule, or something that's nice we could do with integration by parts. Usually it doesn't work out very nice integration by parts, because it doesn't differentiate when it's something's to the power of a half. It doesn't differentiate and integrate very nicely at all. So that's why we probably try and avoid integration by parts with that one. Think about trig substitutions as you go through and practice these questions.